Okay, welcome back to class number 10. Well, actually, welcome to class number 10. I think I'm going to try to abbreviate some of this during class and get it start up as some class 11. Um, because class 11 is already kind of too long. It's got a lot of great content in it, and I want to prioritize that. But let's walk through this video and talk about some of the things that the book had in this section, which is section 3.8, problem analysis and solution techniques. So I would encourage you to follow something similar to this in every one of your engineering courses. Have this mindset and do your best to create a good documentation when you're doing assignments. Quite often, they start with a sketch. We are in a field, engineering, where there's a lot of drawings, and sketching is a important way to communicate between each other, but also a good way to break things down if that we're trying to understand. I have a strong affinity for the free body diagram and in solid mechanics things, but we could also consider what we do here in thermodynamics with the same type of idea, where we want to sketch out the system and label things so we can see like mass flows and heat flows and work rates and that type of thing. And we can it helps us think our way through the problem. And defining what is the thing we're looking at, either like a control mass, like a lump of mass, which is basically what we've kind of limited ourselves to, or a control volume. And so like mass flow can flow through the control volume. So we need to recognize that and assemble our main big equations based on what we draw. And so defining the control mass or the control volume is an important step. And usually we use a dashed line to try to see, to indicate what we consider the boundaries of our control volume and the control surfaces that make that up. We're going to write out the general laws and put down here's the big picture kind of equations. Usually it's going to be the main one is the energy equation, but we'll also have like a mass conservation of mass, or accounting for the different masses coming into or out of the control volume. So like we might have multiple control volumes. I don't really think that's kind of true all that much for stuff that we'll do. I'm going to write down what's going on inside the control volume. So quite often that's going to be a process or a series of processes that we're going to analyze quite often and make a cycle a lot of times within the control volume. So be aware of that. And then you finish the formulation by combining all the equations. I'm not 100% sure I always agree with this. I like to have in-between numbers, but many professors, and I'm not going to argue with it, will like to leave everything as variables until the very end. But this is the general idea that you would want to try to follow when approaching a problem. And I don't know if I have a particular problem in mind that I would want to use as an example. I drew some crazy stuff on my page, and I'm not sure that's worth our time to try to regurgitate what I put on there. Here, I'll show you what I did. I drew up a bunch of things and said, here is the dashed line, and we have masses coming in, mass flow coming in, mass flow coming out. We have heat coming in, maybe we have work coming out across the boundaries. That's what we mean. And then, so I said, okay, here's what they mean by step one. Draw the thing out. So you're thinking what's going on and maybe label the things that you know and decide, here's what I consider my control volume. Like I decided, here's a boundary right here. So the shaft, it crosses this boundary. Therefore, that's how the rate of work or the power that's coming out of the thing. So 3, I wrote down my main equation. Here's my main equation. And there's also underneath it, here's my mass flow, right? So we have 2 sets of mass flows coming in. We have this mass flow, M1, and then it goes out here. I'm saying it's like shooting like some kind of hot liquid over a fan, and it's escaping back over there. I'm just making some crazy machine. And then 4, there's like maybe there's some kind of cycle going on in between there. So these are the processes that I'm talking about inside. And then I combine 5, I combine all the equations and try to find what the main things I want to do. So in the process, and there's no pun intended there, of going through this, you will think, right? This is where the critical thinking takes place. So if you could follow something that starts to approach this way and look for the opportunities to follow these steps. I don't know if I can formally say I would do every one of these things exactly this way every time, but be the mindset of trying to break something down. The sketch and making a good sketch, which I'm not saying mine is a good sketch, but it's not a terrible sketch. I could probably have used a straight edge, which was sitting right here all along. I could probably have used that. But this is a way to not only communicate, but also as an instrument to help you think your way through a problem. So I will do an example in the next video because I already got to the 6-minute mark. I don't know how useful this video is going to be, but I'm going to post it anyway. Stop you. Thank